No.
Can you hear me now?
Yeah, we can.
Yeah. Okay, that's weird. It's supposed to work with this. We'll just do this. All right. You can hear me now? All right, good. I have no idea what's going on. But let's get started because we have a lot to do. So, okay, we are continuing our consideration of population biology now. And this is a very bad time for you to miss class, because this is going to be rich, shall I say. It's going to be complicated. Also, if you don't like math, you are going to be very unhappy for about the next 6 weeks till we get into November. So the final things that we will discuss about populations involve lots and lots of calculations. And we're going to be doing this for a good 6 weeks or so. So today we will start the last two topics in population biology, which are demography and population growth. And we get population growth from demography. So here's the deal. Demography refers to the structure of populations, how many individuals a population has in particular age classes, and how those individuals survive and reproduce. So here are the topics we're going to start today. We may not get through all of them today completely, and that's fine, because the next couple of lectures build on what we're doing today, and they're a little bit shorter than what we're doing today. So we will just we'll just build on as we need to. So the first thing we'll do is do some of the basic terminology: immigration, emigration, mortality, and natality. We'll talk about the types of life tables that we construct in ecology, and then we will get into the calculations. We'll first break the life table into two parts. We'll do the survivorship part first, because we're going to then talk about survivorship curves, which those of you in lab will be constructing later on this semester. Then we'll add in the reproduction part of the life table. But the life table is really a central feature in all of ecology, because it links what happens with individuals to the dynamics of populations. And so what we're going to wind up doing is deriving measures of population growth from the life table. And all of those measures are interrelated. They can all be calculated if you know one of them. It's easier to do it in a particular sequence, which is the way I'm going to emphasize it. But if you know one, you can calculate all the others. So life tables then are a crucial part of ecology because they link individual lives and population dynamics. So they summarize the survival and reproduction for different ages, or in the case of plants, and actually a few animals too, stages within a single population. So, and we'll explain when you want to use ages and when you want to use stages as we go along. So we can derive 4 things from the life table. The first one, net reproductive rate, we derive directly because you just sum up some of the stuff in the life table, and that gives you the net reproductive rate. And that's the number of offspring an individual can expect to have in their lifetime. Okay, but from that, we can get an geometric growth rate, which is the rate of reproduction for a specified period of time. So it's just converting lifetimes into, say, years. We can also calculate generation time, and we can use the generation time, the geometric growth rate, to calculate the per capita growth rate, which is a continuous thing that can be defined over any period of time. So we use calculus for that. Now, this is not a calculus course, and we will be doing very, very limited scary things with calculus. But I will introduce you to a limit theorem from calculus that will help us make that transition. Now, in talking about life tables for the next couple of lectures, we will do something very important. We will simplify our lives greatly by just ignoring immigration and emigration. We're going to say that these are what we call closed populations that do not add or lose individuals due to individuals arriving or leaving. So if you add individuals, they must be born. If you lose individuals, they must die. That helps us immensely starting our discussion of life tables. So here's how we think of life cycles of organisms. Okay, and you're going to see ball and stick diagrams like this repeatedly in this course, but here what you got is 4 ages. Okay, and the 0 age over here at the left is newborns. Okay, newborns survive at a given rate, that's S sub 0, to be 1-year-olds. And of course, I'm using years here just because that's how I think. Could be days, could be weeks, whatever this life cycle is all about. 1-year-olds here on the left survive to be 2 at a rate of S sub 1. So that's the survival rate. Okay, and 2-year-olds then survive to be 3-year-olds with a rate of S sub 2. Now, notice that newborns do not reproduce and 1-year-olds don't reproduce because there's no arrows connecting them with a birth rate, right? But 2-year-olds reproduce at the rate of B sub 2 and 3-year-olds reproduce at the rate of B sub 3. So this is how we basically conceive of life cycles in order to understand them quantitatively. Okay, so we've got stages, 0, 1, 2, and 3, and we've got rates. And the rates here that we've diagrammed are survival rates, S0, 1, and 2, and birth rates, B2 and B3. If you don't have a rate for the birth rate of 1-year-olds, then they don't give birth. They're juveniles. Okay, so we have stages and we have rates. I invite you to consider what happens to the individuals that don't survive from one age to the next. What would be the logical disposition of those individuals? If they don't survive, they die. Yes, exactly. That is a simplifying assumption we are making. We are making the assumption here early on that the only outcomes are that if you survive, that's one outcome. The only alternative is that you die. We will make more complex life cycles later on in which other possibilities can be modeled. So let's talk then about the types of life tables that we actually have. There are really 2 types. And the first one is the static or cross-sectional life table. That's an easy one to get because all you do is either record the age of death of a bunch of individuals, and you can do that by, say, looking at skeletons, or you can just take a sort of a snapshot in time of a population and ask, well, at this instant in time, how many newborns are there? How many 1-year-olds, 2-year-olds, 3-year-olds? Okay, so that's actually fairly easy to do. You can just go census a population and you can estimate what the stages and rates are likely to be. It's a little bit imprecise though, because you have to make the assumption that the distribution of ages don't change over time. And of course, that may not be true. If you have alligators in a swamp and you have a hurricane, well, that's gonna maybe affect the number of adults in that population. And so you cannot always assume that a static table gives you accurate information. And we'll see an illustration of this as we work through life tables. It's easier to work with some kinds of life tables than others. The easier one to work with is actually the dynamic life table. It's a cohort life table, in other words. And what we do is we take a cohort of newborns and we follow them from birth to death. Okay, so we know exactly what the actual rates are. We have no ambiguity about what the survival rate is from age 1 to age 2, because we know exactly what it is. On the other hand, that's really tough to do, especially with long-lived organisms. And so ecologists often rely on these static tables simply because they don't have the ability to construct dynamic tables. If you think of the life cycle of white rhinos in Africa, they live, what, 30, 40 years, maybe more. How long does a National Science Foundation grant last? 2 to 3 years. So you're not going to get a dynamic life table for rhinos with a single NSF grant. You need a lifetime of funding. And that means that a lot of times in ecology, we wind up relying on these static tables, which are easier to get, but have some assumptions and some potential problems, as we will see. All right. Now, let's look at what goes into the life table. So the life table has 2 parts. It has a survivorship part and it has a reproduction part. Let's focus first on the survivorship part. So the survivorship life table has the following things in it. First, it has the number of organisms at any given age, X. So N sub X. N sub 0 is the number of organisms that are newborns, because 0 is being born. N sub 3 is the number of organisms at age 3. And generally, this is what we measure, and then we estimate the rest of these things from the numbers. So the second thing, and one of the really important things about a life table is survivorship, which we say is LX, L sub X. That's the probability of surviving from birth to age X, whatever it is. So for humans, currently L20 is somewhere around 90%, depending on what society you're in. So you have about a 90% chance of surviving from birth to the age of 20 if you're a human. And it's going to be higher in some societies, it's going to be lower in others, but it's from birth to whatever that X is. That's the age. So that's from birth to some age. The next couple of things, however, are from one time period to another time period. So age-specific survival, or S sub X, is the probability of surviving from age X to the next age, X plus 1. So S20 would be the probability of surviving from age 20 to age 21. In North America, that's pretty darn high. It's like in excess of 99%. So it's greater than 0.99. For a lot of organisms, the 1 year survival, though, is a lot lower. For songbirds, it may only be 0.8. Okay, and remember, we're making the assumption that you either survive from 1 year to the next or you die. So the age-specific mortality, and the reason I have two different symbols here is because there's really sort of no agreement among ecologists about what letter to use for this. It kind of depends on who your major professor was in graduate school and what they liked. So you see MX, you see QX, you see DX. I just use MX for mortality. Okay, but don't be fooled. If you see unfamiliar symbols when you're 10 years from now, when you're in graduate school and you're reading papers on demography, you just have to look at the definition. Okay, so MX is the probability of dying in the interval between age X and age X plus 1. So notice that since you either live or die, and currently there are no alternatives to that, SX plus MX must equal 1. That's your first tip in working with life tables. Some things must equal particular things. Since in the basic life table, you either live or die, SX plus MX always equals 1. So if you only have SX, you can easily calculate MX. Just 1 minus SX equals MX. 1 minus MX equals SX. And the final thing in the survivorship part is the life expectancy. And this is by far the most complicated part of the survivorship table. It's the number of years that an organism can expect to live, given that it has reached the age of X. So for humans, E50 would be the number of years that a 50-year-old could expect to live beyond the age of 50. Since current average lifespan in America is about 78 or so, EX for a 50-year-old in America would be something like 28 years. Okay, and I'll show you how we calculate that. So now what I'm going to do is not leave you adrift with these definitions. We're going to work through a sample life table and show you exactly how you calculate these things. So here, what we've got now is our 5 things: survivorship, that's LX, age-specific survival rate, SX, age-specific mortality, MX, and life expectancy, EX. And I'm giving you the numbers of individuals at given ages. Okay, now this, you should understand, this is an example of a cohort life table, a dynamic life table. We actually take a cohort and we follow them from birth to death. You can tell it's a cohort table for one very good reason. If you look at the N column, notice that N starts out large and it drops progressively. And you never get more individuals in a later age class than you had in an earlier age class. This is a really good example of why we like dynamic tables. It makes this much easier to work with. If this were a snapshot in time, you could easily have, say, 100 newborns and then 51-year-olds, 42-year-olds, but you might have 83-year-olds because 3 years before it was a really good year. So a static life table has these built-in issues that we need to take into account. So in order to show you how the life table works, I'm using an example of a dynamic life table that's actually really kind of simple. So here we see the pattern of births and we see the pattern of deaths from birth to the end of life for these 100 individuals. So the first thing to do is to understand that the survivorship from birth to birth is by definition 1. So L sub 0 is always 1. Because if you're born, you survive to be born, right? Okay. This is a promising start. It gets a little more complicated as we go down though. But now, what's the probability that a newborn will survive to age 1? Well, it's simply the number alive at age 1 divided by the number of newborns. So the probability you'll survive to age 1, L sub 1, is 50 divided by 100, or 0.5. And don't worry if this is hard to follow and you're just not getting it all, because guess what I'm going to post after lecture? I'm going to post some practice problems for you, and you'll have the solutions too. And I've got them worked out in great detail about how you go through and do these calculations. Okay, so that's L1. What about L2? Well, L2 is the probability that a newborn will survive to the age of 2. So it's simply the number that are alive at 2 divided by the number of newborns. There's 40 individuals alive at age 2 and 100 newborns. So L2 is 0.4. I want you to notice something else about this life table. The numbers are easy. I really despise hard numbers. This stuff is hard enough without making you carry out 3 decimal points, right, on a calculator. So I try to use easy numbers whenever possible. And if you're ever on a test and you're getting really weird numbers, you're doing it wrong, almost certainly, because I don't like that. There's only 2 columns in the entire life table where that's likely, and I'll show you that. Okay, so that tells us how we get the LX column. Now, what about the SX column? Well, S sub X is the probability of surviving from age X to the following age, X plus 1. So what's the probability that a newborn will survive to age 1? That's S sub 0. The probabilities that a newborn will survive to age 1. Well, it again is the number alive at age 1 divided by the number of newborns. And so that is also 0.5. So notice that L1 is 0.5 and S0 is 0.5. Okay, but then what's S1? That is the probability that a 1-year-old will survive to be 2. And so that, oh, well, yeah, let me just remind you that you generate the mortality by saying what's left over after we survive. Yeah, so 1 minus S0 is M0. So it's 50% survive, 50%. Now let's look at S1. Well, that's the number of individuals that are alive at age 1 and the number that survived at age 2. So what's that fraction? Well, you divide the number alive at age 2 by the number that were alive at age 1. And so now that's 80%. 80% of the 1-year-olds survived to be 2. So that is S1. S2 then is, well, and once again, I put the mortality in there. I keep forgetting that I did that. But again, 1 minus 0.8 gives you the mortality. If they didn't live, they died. So, so on and so on. The number, let's see, S2 here is the number that is alive at age 3 divided by the number that's alive at age 2. That's 30 divided by 40. That's 75%. That's where those numbers come from. And so you can see that the survival column and the mortality column, you add them across, they all add up to 1. 0.75 plus 0.25, 0.66 plus 0.33 with rounding error, of course. 0.5 plus 0.50 plus 1. And so these numbers are fairly easy to figure out. If you're missing something, you can easily calculate whatever is missing. Okay, so let's take an example. If you do not know the number that are alive at age 2, but you know the race, there's multiple ways to calculate that. How do you calculate it? Well, you can take the age-specific survival rate and the number that were alive at age 1. 80% of 50 is 40. So that's one way. Here's another way. L2 is the proportion of newborns that survived age 2. If you know what the fraction L2 is, and you know the number of newborns, just multiply it. And once again, you get 40. So anything that's missing in this table, up to, not including life expectancy, which is a little more complicated, but these 3 columns are really, really easy to generate from one another. All right, if you are missing if you're missing survivorship, you can always calculate survivorship either by dividing the numbers in the n column. If you're missing 0.3, that is L sub 3, you can either divide 30 by 100, which is what we did originally, or notice something else here. The SX column can be multiplied together to generate this. 0.5 times 0.8 is 0.4. 0.4 times 0.75 is, hey, 0.3. Whether or not you have all the information, whether or not you remember exactly how to do it, for a given root, there's always a way to generate any missing numbers. And one of the things I will do with the practice problems is give you some life tables with missing numbers. And it's going to be like a Sudoku or maybe a New York Times crossword puzzle, depending on what analogy you prefer. But you have to look at it as a puzzle. And so this will give you practice in doing these calculations. Okay, before we start life expectancy, do we have any questions so far? All right, I'm going to do this. So just more examples of generating missing numbers. If you don't know S1, notice that S1 is the same thing as L2 divided by L1. There are just, all of these numbers are virtually the same number. If you know some of them, you can always generate the others. Okay, let's look then at life expectancy. How do we calculate life expectancy? Well, let's do the most intuitive one first. Let's do the life expectancy of a newborn. What's the average lifespan of a newborn based on these numbers? Yeah? What? No, we have to wait. What you need to know is the number of years that all of these 100 individuals lived. How many years did these 100 individuals live total? You take, no, it's not, no. So you take however much that is, and then you divide it by 100, and the number of years lived divided by the number of organisms living those years is the average lifespan. So that's what we're going to work through on this. So let's take our 100 individuals and ask, how many died before they got to live even 1 year? Well, that's 50. 50 of them died before they reached the age of 1. So those 50 individuals lived 0 years. Okay, so we had 50 individuals living 0 years, and they lived a total of 0 years. So now we have 50 individuals who are going to live at least 1 year. How many individuals lived 1 year but not 2? It's not right. 10. Because look, 50 individuals reached the age of 1, but only 40 of them reached the age of 2. So 10 of them reached the age of 1, but didn't survive to 2. So 40 plus 10 equals 50. So those 10 individuals lived a total of 10 times 1 is 10 years. All right, how many individuals lived 2 years, but not 3? 10, yes, exactly. Yet 40 individuals lived to the age of 2, and only 30 of them lived to 3. So that means that 10 of them lived 2 years, but not 3. Okay, so they lived a total of 20 years. Each of them lived 2 years. There are 10 of them. They each lived 20 years. Okay, they lived a total of 20 years. Okay, so we're just going to fill this in. So, hey, we've accounted for everybody now. We've asked how many years did these individuals live total, and we knew how many there were at the start. So all we have to do is add up the total number of years that they all lived and divide it by 100, because that's how many there were. So let's add them all up. It's 150. So these 100 individuals lived a total of 150 years. So the life expectancy of a newborn is 1.5 years. How do we get it? Okay, so working through this logically, 50 individuals died before they reached the age of 1. They lived 0 years. 10 lived 1 year, but not 2. So they lived a total of 10 years. 10 lived to be 2 years old, but not 3. So they lived a total of 20. 10 of them lived 3 years, but not 4. So 30 and only 20. And so they lived a total of 30 years. Okay, so this is kind of a really brute force way of calculating this. But I want to show you what exactly we are doing when we do these calculations. And we have a question here in the classroom. Yes?
Okay, I think I figured it out, but I was just thinking, like, from 0 to 1, 60 would like 0.
Okay, so the question is regarding the interval from 0 to 1. Remember, we have 100 newborns at the very start, and we only have 50 of them left by the age of 1. So 50 of them did not live even a single year. They lived 0 years. They died before reaching 1. And then 50 of them lived at least 1 year.
So we don't count them until they die.
We don't count them until they die as we're doing this.
So we could say like that column is like, I guess, yeah, total years lived, or you could say like the ones that died.
Yes, okay, so we're focusing on when these individuals died. That was the question. And so when we calculate the total years lived, we ask how many years did that individual live before it died, and how many individuals did that. So it's kind of, yeah, it's kind of the focus is on when they died. Now, I think you can see that this is okay for the classroom. Can you imagine doing this on an exam? Well, especially if I give you 20 rows. No, I don't think so. So we're gonna, now that we've kind of established what it is that we're actually doing, I'm going to try to make it a lot easier. Another question.
Is the life expectancy 1.5 for all of them?
It's the average. Okay, it doesn't tell you what an individual will actually do. An individual may die instantly, or it may live 5 years, but on average.
Like if you're going to fill out that last column, it would just be 1.5.
Right, so the life expectancy for a newborn then is 1.5. Yes, another question.
Also underneath the 1.5, put a life expectancy for a 1-year-old, or it would just be 1.5.
Okay, that is an excellent question. How do you do the remaining part of this column?
It's the age plus the life expectancy.
Okay, so we're going to work through that right now. You're kind of on the right track, so let's just see exactly how we do it. Now, let's ask what the life expectancy is of an individual that has already reached the age of 1. Okay, so we're starting now with 50 individuals that reach the age of 1. On average, if you are 1 year old, how many extra years do you have to live? Well, we work through it exactly the same way. But we start not with the newborns, because they've already, they're already taken care of. We start with the 1-year-olds. So we get rid of the newborns when we do our calculations. And we just focus on this. So what's the additional years lived? Well, of those 50 1-year-olds, 10 of them died before they reached the age of 2, so they lived 0 additional years. 10 of them lived 1 additional year, but not 2, and so 10 of them lived 1 extra year, that's 10. 10 of them lived 2 additional years, but not 3, so that's 20. So if we add it up again, we get 100 total years lived by 50 individuals. And the life expectancy of a 1-year-old is now 2 years. Okay, and some of you are saying, how is that even possible? It's not possible because life expectancy can't get higher, can it? Actually, it can. If you look at this population, you'll see that most of the death occurs between 0 and 1. So if you live to be 1, you have a lower probability of dying in each of the succeeding years. So yes, life expectancy can go up. In fact, some really interesting research suggests that when animals reach extremely old ages, their life expectancy actually increases. So if you live to be 70, your life expectancy is 8 or 9 years. But if you live to 80, your life expectancy is maybe another 10 years, which is really weird. But that's the way it is. And we had a question in class back there.
So like in that African individual, the population died 0.1, is that almost like an outlier?
It's not an outlier. So the question is this high mortality between 0 and 1 like an outlier? It's just the pattern in this population. And the fact is that if the average life expectancy is 1.5 years and half of your individuals die before ever reaching 1 year of age, then the remaining individuals have to live longer than you might expect in order to make that average 1.5. So you just have to look at these tables for what they are. Moving on to say E2, how many years additional can a 2-year-old expect to live? Well, we do the same thing. We get rid of the 1-year-olds and we base our calculations on a starting number of 40. And so that gives us 60 years total that these 40 individuals live. And so the life expectancy is back to 1.5. So this is what that total table would look like. And of course, at the end of life, at the very end of life, regardless if your life expectancy does go up at some point, it's going to go down. It's going to go down to 0 eventually. But don't be suckered into thinking that life expectancy is highest for newborns, because it's not always. Okay. Life expectancy is harder conceptual. It takes more work to calculate. So when I give you a problem on the exam and I ask you to calculate a life expectancy value, it's worth more points than LX or SX or MX, because it's more complicated. Now, we have gone through this process here of doing this calculation, and ecologists don't do that. We look for a shortcut, and by God, there's a shortcut. Life expectancy is always the sum of the LX column from x plus 1 to infinity divided by LX. So let's take the newborns. E0 then is the sum of the LX column from 1 to infinity, which is outlined in red here, divided by L0. So E0 is all of these numbers added together divided by 1. And of course, what you see is 0.5 plus 0.4 plus 0.3 plus 0.2 plus 0.1 is 1.5 divided by 1 is 1.5. So whenever you're looking for a life expectancy, an EX value, you add up the LX column starting with the next age, and then you divide it by LX for the missing age. So here's how you do L1. You add up L2, L3, L4, and L5, and you divide it by L1. So L, what's that?
Disregard like L0.
This is for individuals that have already reached the age of 1, so you don't deal with the newborns, no. Okay, so 0.4 plus 0.3 plus 0.2 plus 0.1 is 1.0. And what's L1? It's 0.5. 1 divided by 0.5 is 2. And that, my friends, is the life expectancy of a 1-year-old. It's 2, as you see in the column on the right. Okay, let's very, very quickly end this part by talking very briefly about survivorship curves. So we've seen these patterns of survivorship and mortality. They tell us quite a lot about organisms, and there are 3 basic types. In type 1, most of the mortality occurs among older individuals. That's us. So yeah, we have some mortality at young ages, but mostly we live a long time and then everybody croaks all at once. Okay, an example of that is doll sheep. That was the original life table that anybody ever put together. Type 2 is a constant rate of survival. So every year you lose 80%, 80%, 80%, 80%. Songbirds are a really good example of that. And then type 3 is where you have extremely high mortality among newborns, but if you can get past that age, you can live for a very long time. Sea turtles, redwood trees. Okay, so here are some examples of that. Here's a cartoon that compares them. And notice that we've got a log axis here. You'll always see a log axis on the y-axis when we graph these curves. Okay, because that makes them way more comparable. And it also straightens out the type 2 curve so that it's kind of constant. It's a nice line. Okay, here's doll sheep. This was the first life table anybody ever put together. And then what they did was look at the skulls of dead sheep, and they did some calculations based on that, got a static life table, and they were able to then to graph the graph at the bottom here that shows you that most of the mortality occurs late in life. There's a little bit of mortality up here because it's a log axis. So you see it decreases from 1,000 to about 800. So that's substantial. But then after that, it's pretty constant until you get older. And then everybody grows. Okay, and the other thing to notice about these curves is that we always kind of standardize them to start at 1,000 and go down to 1, because that makes it easy to compare different species that have very different kinds of curves. So we always try to standard. If we have 11,200 individuals in our life table, we divide that then by 11,200 and multiply by 1,000, so that we always start with a starting number of 1,000. So here are some examples. Here's some type 1 curves for rotifers. Notice that these guys on the top left have a fairly substantial mortality early, but then it's constant. And then when they reach the age of about 48 weeks, boy, everybody just dies. That's a good type 1 curve. Okay, notice that they're not perfect. They don't correspond perfectly. At the bottom left here, you see another. Wait a minute. Oh, this is phlox. These are phlox plants. Okay, so top is phlox. Here's the rotifers down here. It's not so perfect. Kind of starts downhill sooner than we'd like to see for a perfect type 1 curve, but it's more or less type 1. In the middle, you have some animals that have a constant rate of mortality. Here's white-crowned sparrows and robins, and notice that the probability of death is the same every single year. Straight line. Okay, and here are mud turtles. These are not sea turtles at the bottom in the middle. These are mud turtles. And once you get past this initial mortality, it's pretty much constant the rest of their lives. On the right, you see a type 3 curve, a little tiny flowering plant. Notice that you start with 1 million seeds. We just had to deal with that. We couldn't standardize it to 1,000, so oh well. But notice that you produce 1 million seeds and you wind up with maybe, 30 individuals surviving for 1 year. And then after that, though, notice that the guys that survive at least 1 year survive for a fairly long time. So these are survivorship curves. They're a graphical way of depicting what's in the life table for the survivorship part. It's really a valuable tool for us. And we're gonna kind of stop here. I'm gonna post some life table problems for you to work on. I'll post the answers as well. Do try to work through them before you look at the answers though. You'll get this very kind of problem on the exam. So pay attention to it. And I think that's all we're going to do for today. We'll pick this up next time with the complete life table.
Thank you.
All right, guys, at home.
Thank you, Dr. Howard.
All right, I'm going to log you all off. And we'll see you Monday, hopefully. Or if you're in lab, I'll see you in about an hour.